Right now, if you ask an AI to design a completely new physical material, it will likely just spit out a mathematical fever dream.
Yeah, totally.
Yeah.
It might design a crystal that, looks beautiful on a screen.
Right, but the second you actually try to synthesize it in the real world, the atoms would just repel each other and
The whole thing physically shatters. Exactly.
right. But what if we could put guardrails on that AI's imagination? Welcome to the deep dive. Today, we're looking at how scientists are forcing AI to hallucinate the exact stable quantum geometries we need to build a subatomic internet for you.
It really is a profound shift in how we approach physics. Like, we're moving from simply observing the quantum realm to deliberately architecting it, atom by atom.
And to figure out how that's even possible, we are looking at two highly technical sources you sent us. The first is it's a dense physics paper called Dressed Interference in Giant Superatoms.
As a mouthful.
Yeah, it really is. And the second is a briefing on a generative machine learning framework known as SCIGEN, which stands for Structural Constraint Integration in Generative Models.
And, I mean, they seem totally disconnected at first glance,
Yeah,
right?
really.
Because one is purely theoretical quantum optics, figuring out how data moves, and the other is applied AI, figuring out how to generate physical structures.
Right.
But they are actually two halves of the exact same puzzle.
And that's our mission today. We are going to explore how scientists are drawing up the blueprints to route quantum information on a subatomic level, and then how they are using this new AI framework to invent the exotic physical materials required to actually build those blueprints.
Which is a huge undertaking.
Exactly. And to help me translate the heavy mathematics here, I have our resident expert.
Glad to be here. My goal today is to help you see the underlying mechanisms. We aren't just going to talk about what these quantum networks are.
Right.
We're going to look at exactly how they work and why they matter for the future of computing.
Let's start with the physics side, because before we can build the materials of the future, we have to understand how quantum data is supposed to move through them, right?
Right, that's the foundation.
So the first source introduces this wild concept, the giant superatom. Okay, let's unpack this. I've heard of atoms, obviously, but what exactly makes an atom giant? And more importantly, how does it become a superatom?
Well, let's ground this in the environment first. Imagine a waveguide.
Okay.
In quantum optics, a waveguide is essentially a microscopic channel. It's like a tiny fiber optic cable that carries quantum light or photons.
Got it.
Normally, an atom is incredibly small compared to the electromagnetic waves in that channel. So it interacts with the waveguide at a single localized point.
Just one point.
Yeah, it's like a single speck of dust sitting on a guitar string. But a giant atom is engineered differently. It's physically designed to couple to that waveguide at multiple spatially separated points.
Wait, so instead of just being a speck of dust, it's physically straddling the cable, like touching it in several different places at once.
Precisely. And because it touches the channel at multiple points, the quantum waves it emits or absorbs travel down the channel and actually interfere with each other.
Oh, wow.
Yeah, it creates self-interference. So depending on the distance between those coupling points, the atom's waves can amplify each other or they can cancel each other out.
Okay.
But the authors of this paper didn't stop at a giant atom. They created a giant superatom, or GSA.
Right, they leveled up the complexity, so what's the difference there?
A giant superatom consists of two or more atoms that are quantumly entangled and interacting directly with each other.
Okay.
They exchange energy at a very specific mathematical rate, which the paper refers to as J. But here's the critical mechanism. This entire entangled group is collectively coupled to the waveguide through only one of the atoms.
Let me see if I'm picturing this right. It's like a highly classified corporate partnership.
Okay, I like where this is going.
You have two executives, the atoms, sitting in a secure room, constantly whispering secrets back and forth. They're deeply intertwined. But when it's time to release a public statement, only one of those executives acts as the spokesperson. And that spokesperson is talking to the outside world, the waveguide, through multiple different microphones placed at different distances.
That is a perfect way to visualize it. The two atoms share the internal quantum state, but the external environment only interacts with the spokesperson atom.
That's wild.
It is. And mechanically, this setup creates what physicists call dressed eigenstates.
Yeah, the paper mentions these dress states constantly. The symmetric state, which they call the plus state, and the antisymmetric state, the minus state. But why do these states matter? What do they actually do?
What's fascinating here is that they allow for state-selective self-interference.
Meaning.
Because of how the waves interact at those multiple microphones,
Mm.
the superatom behaves completely differently depending on whether it's in the plus or minus state. If you tune the distance between the microphones just right, one of those states becomes perfectly dark,
Dark, meaning what, it just turns off.
meaning it becomes decoherence-free. Normally, keeping a quantum state intact is like trying to carry water in a sieve.
It just leaks out everywhere.
Exactly. It naturally wants to leak its energy and information into the surrounding environment. But in a dark state, the self-interference perfectly cancels out that leakage.
Oh, wow.
Yeah, the superatom just shuts the door and holds onto its quantum secret perfectly. Conversely, the other state will rapidly decay and broadcast its energy into the waveguide.
So based purely on its internal state, it can either lock data in an impenetrable vault or instantly broadcast it.
Exactly.
That's an incredible mechanism for a single node. But for you, the listener, who is going to want to use a quantum internet to send secure data across the globe, one isolated vault isn't enough.
Right, you need a whole system.
Exactly, we need to route traffic. So how do we actually turn this into a network?
That brings us to the architecture of braided structures. Yeah. Imagine taking a second giant superatom and placing it alongside the first one. But you interlock their coupling points. The microphones of the first spokesperson atom overlap with the microphones of the second.
Like weaving them together along the same physical cable.
Exactly. And because you can tune these states to be dark, you can transfer the internal entangled state from the first superatom to the second without a single drop of quantum information leaking into the waveguide.
So it's a flawless handoff.
It's a flawless handoff. The paper shows that if you chain enough of these braided structures together, you create a structured entanglement lattice, specifically something called a Su-Schrieffer-Heeger, or SSH chain,
Okay.
which supports topological edge states.
Whoa, wait, SSH chain, topological edge states. You totally lost me there. What does that actually look like for the data?
Okay, think of it like a row of dominoes. Normally, any domino can be knocked over by the environment. But in an SSH chain, the specific geometry of how the superatoms are braided physically alters the math of the system. It creates a scenario where the data stored on the very edges of the chain is mathematically prohibited from decaying.
Prohibited from decaying.
Yes. The data is protected not by a software firewall, but by the physical geometry of the network itself.
Okay, that makes sense. The shape itself is the armor. But braiding requires the superatoms to be physically intertwined, right?
Right, they have to be close.
So what if we want to send data across a distance, like from one city to another? The source dives into separate GSAs when the superatoms are far apart.
Yes, and they introduced this concept called chiral spontaneous emission.
Yeah, here's where it gets really interesting.
It is arguably the most powerful mechanism in the paper. When superatoms are physically separated, you can tune the phase difference between the coupling points.
Essentially tweaking the delay between the microphones.
Exactly. And when you do this, you break the time reversal symmetry of the interaction.
Hold on. Break time reversal symmetry. Are we building a time machine here? What does that actually mean mechanically?
I know it sounds like sci-fi, but it's really about the symmetry of direction over time.
Okay.
Imagine dropping a pebble in a perfectly still pond.
Sure.
The ripples travel outward in all directions equally. If you reverse time, they would contract equally. That's symmetrical.
Right.
Breaking time reversal symmetry in this context means the atom drops its quantum pebble, but the ripple only travels left, never right.
Wait, so by tweaking the phase of the spokesperson atom, the superatom acts like a quantum traffic cop.
Yes, exactly.
It can force the symmetric plus state to only emit photons to the left, and the antisymmetric minus state to only emit photons to the right.
That is exactly what happens. It selectively routes the excitation directionally.
But why is that specific traffic cop ability such a big deal?
Because it allows for the remote generation of W-class entangled states.
Which are what, exactly?
Well, entangling two particles right next to each other is hard enough. Entangling three or more particles across a large distance, which is multipartite entanglement, is historically a nightmare.
The system just usually collapses, right?
Exactly. But because chiral emission guarantees that the photon carrying the entangled state travels in exactly one predetermined direction, you can deterministically distribute that entanglement to other distant superatoms with incredibly high fidelity. It is the holy grail for a stable, scalable quantum internet.
Okay, so we have this beautiful, flawless math. We know exactly how to route internet traffic using topological edge states and chiral emission.
On paper, yes.
Right. But math doesn't route traffic, physical servers do. And this is where the narrative shifts. Because when physicists take these blueprints to material scientists and say, hey, build me a W-class quantum traffic hop, they hit a massive wall.
An almost insurmountable wall.
Oh.
To physically realize a waveguide or a braided lattice that supports these exotic effects, we need materials with highly specific, incredibly rare atomic geometries.
Right. Like, for example, the sources constantly mention needing a Kagome lattice.
Yes.
Which, from my understanding, is an atomic structure that looks like a traditional woven Japanese basket, a pattern of interlaced triangles and hexagons.
That's right.
And in physics, this specific shape causes something called frustrated magnetism.
Yeah. In a normal material, magnetic spins like to alternate up, down, up, down.
This is simple enough.
But in the triangles of a Kagome lattice, if two atoms are pointing opposite ways, the third atom is frustrated. It doesn't know which way to point.
Because both options break the pattern.
Exactly. And this indecision creates massive quantum fluctuations that are highly desirable for advanced quantum networks.
But finding a material in nature that naturally forms a perfect Kagome lattice and doesn't fall apart at room temperature is like finding a needle in 1,000 haystacks.
It's nearly impossible.
So why couldn't scientists just ask standard AI to invent one for them?
Because traditional generative machine learning doesn't inherently understand the strict laws of physics or geometry. It understands statistical averages.
Okay.
If you train a standard AI on a massive database of known materials, it will spit out new materials that look generally similar to the bulk of that database.
It just interpolates.
Right. But if you beg it for a specific, rigid geometric constraint, like a perfect Kagome pattern, it struggles. It will either ignore your constraint entirely, or it will output a structure that is so chemically unstable, it would literally snap apart the moment you tried to synthesize it.
It's basically hallucinating a pretty picture without understanding the load-bearing walls.
Exactly.
Which brings us to our second source, SCIGEN, structural constraint integration in generative models. This is the AI framework that finally breaks the bottleneck.
SCIGEN is a brilliant leap forward. It is a plug-and-play framework designed to work with existing diffusion models, like diffCSP.
Okay, so it plugs in.
Yeah. What it does is allow researchers to forcibly inject non-negotiable geometric and symmetry constraints into the AI without having to retrain the entire multi-million-dollar AI model from scratch.
That's huge. And I was reading through the methodology of how they actually force that constraint, and I want to try a new analogy here.
Okay, let's hear it.
Since diffusion models work by denoising pure static light, trying to clear up the fog on a cloudy window to reveal a picture, is SCIGEN essentially putting a highly specific, unbreakable stencil on the glass.
Oh, I see.
Like the AI is allowed to clear the fog and draw whatever atoms it wants everywhere else, but it absolutely must leave the exact shape of your Kagome stencil intact.
That is a highly accurate way to visualize it. SCIGEN uses a mathematical process called strategic masking.
Strategic masking?
Right. During the generative process, it mathematically splits the generation into two parts. The constrained components, your stencil, and the unconstrained components, the fog the AI is allowed to clear.
So the AI is still doing its creative denoising magic, but within strict physical boundaries.
Exactly. The target geometric constraint is infused with noise, just like the rest of the model. But during every single step of the denoising process, SCIGEN applies a binary mask.
And what does that mask do?
This mask perfectly merges your predefined rigid structure with the unconstrained atoms the AI is creatively placing. And mathematically, it performs conditional sampling.
Meaning it checks its work.
Yes. It constantly checks back with the base model's original understanding of physics to ensure that the bonds connecting your rigid stencil to the new atoms are actually realistic.
See, theories are amazing, but for you listening right now, the real question is, did this actually work?
Oh, it worked.
Let's look at the staggering scale of the testing here. The briefing states that using SCIGEN, they generated 7.87 million compounds using Archimedean lattices as the structural constraint. Almost 8 million AI-generated candidates.
Which is an astonishing volume. But as we discussed, volume means nothing if the materials are just mathematical fever dreams. To prove these materials could actually exist in the real world, the researchers forced these candidates through a brutal, rigorous, 4-stage pre-screening gauntlet.
I want to break this gauntlet down because it really highlights the difference between AI hype and rigorous science. So what was step one?
Step 1 was charge neutrality. Using an approach called SMACT, they looked at the oxidation states of the atoms. Basically, they asked a simple chemistry question. Do the electrical charges of these newly combined elements balance out to zero?
And if they don't?
If not, the material is highly reactive and impossible to stabilize. Millions were discarded right there.
Wow. Okay, what about step 2?
Step 2 was space occupancy. They calculated the ratio of atomic volume to the volume of the unit cell.
Essentially checking if the AI accidentally tried to cram 2 atoms into the exact same physical space.
Exactly.
If the ratio was greater than 1.7, it meant impossible physical overlapping, so those went straight in the trash.
Correct. Now, step 3 is where it gets really advanced. They used a graph neural network, or GNN, to predict stability by checking something called the energy above the convex hull.
Okay.
They needed it to be less than 0.1 electron volts.
Okay, let me pause you there. Energy above the convex hull. Explain that mechanism. How does a graph neural network figure that out, and why does 0.1 electron volts matter?
Well, the AI maps the proposed atoms and their bonds like a complex 3D webograph. It calculates how much potential energy is pent up in those specific bonds. Think of the convex hull as the absolute floor of energetic stability for a group of elements.
A baseline, basically.
If the new material's energy is too high above that floor, it's like a tightly coiled spring.
Ah.
The moment you synthesize it in a lab, that spring will violently uncoil, and the material will immediately degrade into a different lower energy substance.
It just falls apart.
Yeah. So by mandating it stay below 0.1 electron volts, they ensure the material is physically relaxed and stable.
That makes perfect sense. And the final step, step 4, was GNN realism. They used another classifier to scan the surviving structures and filter out any weird, unrealistic distortions.
Right, or lingering Gaussian noise left over from the diffusion process. They only kept the pristine structures.
And the survival rate of this gauntlet was unprecedented. Over 10% of the generated materials, which is more than 790,000 compounds, passed all 4 stages.
It's a massive number. But they didn't stop there.
Right, they had to prove it further.
They took a sample size of 26,000 of those survivors and subjected them to density functional theory, or DFT, calculations.
And DFT is basically the gold standard of computational physics, right? Like,
Oh, yeah.
it literally models the quantum mechanical behavior of every single electron in the material to see if it holds together.
Yeah.
It takes massive supercomputer power to run.
It does. And over 50% of the SCIGEN candidates successfully optimized and proved stable under DFT.
That's unbelievable.
The AI actually did it. It hallucinated completely novel materials that adhered to strict quantum geometries, and the physics held up.
And there was one massive, specific breakthrough highlighted in the source. They successfully generated stable materials using a Lieb-like lattice, populating it with magnetic atoms, specifically terbium and dysprosium.
Yeah, and if we connect this to the bigger picture, the Lieb lattice is a variation of a square lattice, but its specific geometry is famous for causing destructive quantum interference.
Destructive interference.
Yeah. When electrons try to move through this lattice, the interference waves perfectly cancel out their movement.
So the destructive interference in that Lieb lattice essentially traps the electrons.
Exactly.
They can't gain or lose energy, which creates this perfect, frictionless state called an electronic flat band.
Right.
And we know from other fields that flat bands are the magic ingredient for high-temperature superconductivity. Like, it creates an environment where quantum effects can survive without being destroyed by heat or electrical resistance.
Which is exactly why we need SCIGEN.
Yeah.
Because you can't just stumble upon a shape that perfect in nature. SCIGEN guarantees the shape while preserving the stability. In fact, the briefing document explicitly confirms this. Let me check the exact phrasing. Yeah, it says, SCIGEN effectively performs conditional generation with respect to the distribution of the base model, ensuring the constraint set by SCIGEN preserves the integrity of the base generative model.
Including the stability of the generated materials.
Exactly. They successfully merged the unyielding laws of physics with the boundless creativity of AI.
So what does this all mean? For you, the listener, it means we are in the middle of a massive, quiet paradigm shift.
Definitely.
We are moving away from database-driven discovery, where scientists are essentially just digging through the dirt, hoping to stumble upon a useful crystal. We are moving into the era of constraint-driven design. We are literally ordering quantum materials off a menu.
It's completely revolutionary.
We say, I need a Kagome lattice that is chemically stable and supports topological edge states, and the AI delivers the blueprint.
And this is exactly how our two sources synthesize. The first paper gave us the theoretical architecture.
The braided giant superatoms.
Right. The chiral routing traffic cops, the secure quantum vaults, but they were just theoretical blueprints without a physical substrate.
And SCIGEN gives us the physical materials with the exact geometries required to actually construct those superatom networks.
The AI provides the tangible hardware. The physics provides the quantum software.
It's an incredible synergy. And I want to leave you with a final thought to mull over, something to explore long after this deep dive ends. If an AI framework like SCIGEN can now successfully hallucinate, validate, and stabilize the exact complex atomic structures needed for futuristic physics, what happens when we remove the middleman?
That's the real question.
Right. What happens when we feed the mathematical requirements of a giant superatom's J coupling rate directly into SCIGEN as the primary constraint? Could an AI design the absolute perfect physical housing for a quantum internet, optimized down to the single atom, before human engineers even figure out how to synthesize it in the lab?
It's a very real possibility.
Are we rapidly approaching a closed loop of automated quantum design where the AI invents the hardware it needs to run its own quantum calculations?
It raises a profound question about the pace of our innovation. We are crossing a threshold where the limiting factor in quantum computing is no longer human imagination. It's simply our mechanical ability to print the physical blueprints the AI has already perfected.
From a world where we passively observe quantum mechanics, to forcibly architecting it, to automating the architects themselves, thank you so much for sending in such incredible source material. And as always, keep questioning the world around you.